Okay, looks like we're ready to start the first session after lunch. Um, I might invite people to come down a bit closer because I'm going to be giving some demos and stuff. I think it's going to be super hard to see if we don't get a bit closer, especially when we come to like the web demos. So given there aren't many of us, just get as close as you can. And I think so this isn't really going to follow the format of a kind of tutorial. It's a slightly different presentation, but we'll keep it quite informal. So definitely jump in if you've got any questions or if there's some kind of outlandish assumption I'm making that you want to question, dive in there. Okay, so I'll introduce myself. My name is Roly Pereira. I'm one of the researchers at ICCS. So we have quite a large team of research software engineers at ICCS who work with Vesri projects. We also have 5 researchers who work in kind of earth sciences and machine learning and so on. So my research is more about the kind of front end of climate science. So I'm more interested in how we can communicate and explain climate science in a more kind of transparent way. So what we're going to be talking about today is a programming language called Fluid. So the one sentence summary is that Fluid is a functional programming language for building transparent, self-explanatory research outputs. So the basic structure of the session is going to be sort of 10 minutes or so where I kind of motivate the idea, explain what the problem is as we see it, and how we see Fluid as fitting into, part of the solution to that problem. And then we'll probably spend most of the talk on some examples where I'll show you some code written in Fluid, what the kind of visualizations look like, what that's like for if you're a kind of end user or a consumer or reader of those visualizations. And we'll see a bit about what it's like to create them as well. And then there'll be some discussion about future directions. And some of the examples are also showing you some stuff that's work in progress. And then a little bit about how you could try this out on your own research if you're interested. So as I said, this is very much work in progress as a project. Let's treat it as informal. So just, if you've got any questions or sort of anything you want clarification on, just jump in. Okay, so we form beliefs and make decisions about the world using data. And that data is being curated into charts, figures, and text by journalists and scientists. So we heard a lot about the IPCC earlier. This is from Assessment Report 6, which Tamsin mentioned. This is Working Group 1. So this is the working group that do the kind of core science, if you like. And these are a couple of figures taken from the summary for policymakers. So we can see some interesting information being presented, but it's not necessarily clear what we're looking at. Where did these things come from? Why should we trust what's being claimed? What even is being claimed? So on the left, there are some legends and captions, but they may only have limited value. And of course, there's text that comes along with these things. They aren't just sitting there in isolation, but the text itself has a lot of references to computed data. So there are all kinds of numbers that appear in the text. Where did they come from? How do they relate to the charts and the original data and so forth? So this is a challenge, whether you're a scientist trying to make sense of the work of your colleagues, whether you're a policy maker trying to come up with some kind of policy that's supposedly informed by this report, whether you're a journalist trying to communicate to the general public or an educator, or indeed if you're just a random person trying to make sense of the world around you, this is a kind of challenge. So this is to be expected in a way, the kind of opacity of these things for traditional print media like newspapers and traditional PDFs, for example. But we're increasingly living in a digital world. So can we do things differently in this setting? And in particular, our research question is how can programming languages themselves help with this picture, help improve things? So of course, this isn't a problem that just extends to policymakers. As we've already alluded, we have research papers and kind of news articles and so on. So if, for example, I'm looking at this paper, there may be, this is very small, sorry. So that says control. So there may be data sets, for example, that are being alluded to in a figure. What is that data set? Where can I find it? There may be visual features whose meaning is a bit obscure. There may be different channels of visual information, and it might not be obvious what they're intended to represent. Or if I'm looking at this is a BBC visual journalism article where it's projecting how the climate in Bristol is going to change. Again, this is actually very hard to see, but there may be technical terms like rolling average. It might not be obvious what that means. Or there could be an allusion to other elements of the data set. So actually what you can't see here, so this is plotting some kind of temperature moving average, but there are actually lots of little pixels, which are sort of very faint and basically impossible to see, but they're obviously an allusion to something. So are they supposed to be useful? Are they telling us something? What are they? And finally, this is an interactive climate simulation from MIT called En-ROADS. So this allows you to kind of twiddle various sliders and see what the impact of certain policies is going to be on projected climate forecasts. And presumably here at some point you transition from observational data to projected data, but it's not actually clear where that transition happens because you don't necessarily know when this system was built. And it's not really clear what parameters are being changed when you twiddle these sliders. What's the science that underpins this? What's the data and so on? So in some sense, these challenges are intrinsic to what these artifacts are actually trying to do. They're trying to condense a complex situation into a simple narrative. So we're always going to be trading off this kind of high-level story from the kind of underlying detail. But we can do better than, potentially do better than just having these completely opaque artifacts. So with these things, there's no way to peek under the hood and see what's going on. So that means they're hard to interpret and verify and trust. Okay, so open science and fair data and so forth, in a sense, is a response to this kind of problem. The idea being that if we could have access to the raw materials that we use to derive these lovely artifacts, then perhaps we could reconstruct the results for ourselves. We could maybe challenge some of the findings in the paper, for example, if we could access the code and the data. So if we have some open science, like maybe this paper on the left, and it's open science, that means we can potentially go and download the data and the source code associated with the paper. But even getting that running again can be quite a challenge. It's not obvious that just having the raw materials is actually going to help us do much. And if we're talking about actually understanding the relationship between these raw materials and the kind of context we were in when we were trying to make sense of something, then that's an even harder proposition. So this white paper by the Royal Society from 2012 does quite a nice job, I think, of setting out the actual criteria that we're interested in when we talk about open science, understood as a kind of social enterprise. And the case they make in this white paper is that the openness criteria we actually make that we actually care about are ergonomic in nature. So we're interested in kind of intelligibility, ease of criticism, engagement, accessibility, and so on, rather than just the kind of structural properties that things like fair data have sort of focused on. So one way to frame this is as a disconnect between data and discourse. So we have the kind of world where we do the science, and then we have the world where we communicate the science to our peers and so forth. And those two worlds are quite separated. So as a software person, I like to think of this as a software infrastructure problem. So computational notebooks like CurveNote and Mist and Jupyter and so on that you'll probably be familiar with take a step in the direction of kind of making outputs or breaking down this disconnect, if you like. So in a notebook, rather than just having a single output, you break your pipeline down into individual steps. You might document several intermediate artifacts that are of interest. You might attach visualizations to so on to each of those. And then you might weave additional narrative around those individual intermediate artifacts and sort of tell a story about what your system does. So that's an important step, and I think it does start to address some of this disconnect. So what we're interested in this project is another kind of dimension, if you like, of this sort of transparency picture. So what we're interested in here is what we call transparent programming languages. So a transparent language is a language where instead of just running the artifacts and using them to produce a kind of final output, you kind of bundle all the artifacts into all the intermediate stuff into the final output, and you track the provenance between different parts of data, the input and the output, and so on, and you preserve it into the output. And you do that in such a way that you can then give the reader sort of more information about what they're actually interacting with. So this is unlikely to be feasible for a whole kind of climate science pipeline. It's not going to be possible to do this for kind of a physics simulation, for example. It's probably not obvious even what it would be like to do that at that level. But for the more user-facing parts, where we actually start communicating the results of these models to people, then there's some opportunities potentially to do things differently. Okay, so I'm going to let you think about that, and I'm going to go to an example now. So does anyone want to jump in with any thoughts or questions at this stage? I mean, maybe if I show you kind of the basic idea, then maybe then you can start to ask a few things. So what we're looking at here, how small is this? Might be able to go a bit bigger. Okay, so we're looking at some non-renewable energy data. On the left, we have this stack bar chart showing renewable energy output for various countries. On the right, we have nuclear output plotted against nuclear capacity. And on the left, we have a bit of a legend that's kind of telling us something about what's going on the right. We don't have a lot of information. We have some axes. So this idea of kind of bundling up the kind of pipeline and preserving it into the output means that when we take a fluid program and we turn it into a visualization like this, one of the things we can do is provide a view of the underlying data set. So I might have to make this smaller. Okay. So I'll show you how this kind of is, what this is like for a reader first, and then we can look at the kind of fluid code used to create this. So the first thing to notice is that on the left, we're only showing 20 records out of the data set, which had 60 records. And we're able to do that because we're tracking how the data flows through the computation. And it turns out that in these two charts, we only need those 20 rows. So we can provide this kind of filtered view of the data already. And then one of the things you might do is interact with this column, so the nuclear capacity column. So as we move around in the data, we'll see that this might be a bit hard to see, but there are various scatter plot points on the right are being highlighted as I move around. So as I interact with different parts of the data, different parts of the output are being highlighted. And what's going on is that the data that my mouse is currently over is being consumed by that scatter plot on the right. So in order to compute that scatter plot point, I have to use this particular data value. So that's why we're highlighting it. And then the reason we get these other three pieces of data highlighted is that in order to plot that scatter plot point, we actually needed these other pieces of input as well. So we've got a little bit of context here that's telling us that in order to sort of interpret this 59.39, we also needed these other bits of data. So in this case, it's actually only the y coordinate of the point that's being highlighted, that's consuming this data. And that's not apparent from the user interface, so it's kind of impartial information, but it's giving us some sense of what's going on. For example, we can probably guess that each point on the right corresponds to one of the years, for example, because we can see that we're consuming all data from the same year. And in this case, we've just added them together. And we can make that visually slightly clearer if we just click on this data element on the left. So that creates what we call a persistent selection. So now I've expressed interest in this. This is my kind of primary selection, is that 50.63. And the three numbers that are highlighted in gray are a kind of secondary selection. They're the other bits of data that are relevant to that. Now, if I go over to the right-hand side and interact with this point, I can see now all the data needed for that point. So this, as I mentioned, the user interface doesn't distinguish between the X and Y coordinates of the point. So when I move my mouse over it, I'm effectively expressing interest in both of those coordinates. So in order to compute the X and the Y coordinates of the point, I had to use all 8 data elements there. And if we go back over here and interact, for example, with nuclear output, then we'll see indeed that the same point is also highlighted over on the right. And we might sort of guess now that those numbers, those 4 highlighted numbers in nuclear output, were used to compute the X coordinate of the point on the right. If you just kind of add them up, they correspond roughly to what we're looking at on the X axis. But now that makes it look like the axis labels are actually potentially incorrect, because it's nuclear output data that we're looking at here, and it's actually being labeled with nuclear capacity, that axis. Okay, so again, this is impartial information, but it's giving us a bit of visibility onto what's going on here. The other thing to notice is that we picked out a row of data here as well, which is interesting. And perhaps you can see that if I move around in this column, there's a little bit of sort of very subtle highlighting moving around on the bar chart. People see that? I think if I drag it, it's a bit more visible. So what's going on there is we've got the same piece of data that's being used by 2 different charts in 2 different ways. So we can investigate that again by moving over to the right-hand side, and we could try, or we could just first of all move around and see that each segment in the bar is using those 4 elements, the coal, gas, nuclear, and petrol output for a particular country. And that helps us see, for example, that nuclear output is being treated as a non-renewable, which might not be obvious, I guess. You might also notice that as I'm moving around in the bar chart, that the scatter plot points are also being highlighted on the right. And that's pointing to a kind of shared data dependency, because even though these are 2 different sort of views of the same data, they do overlap. And we can investigate that by, say, clicking on a couple of these bars on the left. So that makes that into a persistent selection. And then we can move over to the scatter plot points. And if we move our mouse over one of the highlighted points, we can see that it's got an overlapping data usage. So this tells us that that single value of nuclear output is actually needed to plot both a scatter plot point on the right and one of the selected bars on the left. Whereas if we move our mouse over the other points, we can see that they don't have any overlapping data. So if you're familiar with data visualization techniques, this is what's called sometimes brushing and linking. So brushing and linking is when you have 2 selections in different charts that are kind of sort of coordinated in some way. But here we're able to do it in a transparent way. We're able to explain why these segments of the bar chart are related to various points in the scatter plot and the reason is that they have these overlapping kind of data usage. Okay. So that's the basic idea. And the key sort of takeaway is that the user hasn't had to program any of these interactions themselves. So the way it works is the user creates a visualization in Fluid, which is a functional programming language, and then everything else is kind of taken care of. So it's a fairly straightforward language. I'll just highlight a couple of things. So it has lists and list comprehensions. For example, this is similar to what you would do in Python, except with a slightly different notation. And then it has dictionaries, also similar to Python. And the idea is that the programmer just describes how to map data to visual elements. And then the Fluid runtime is going to analyze the dependencies and add interactions that allow the user to explore interactively the kind of relationship between inputs and outputs. And then the user is able to formulate these kind of queries by just interacting with the output. Okay, so I'm going to give you one more example, and then we'll come back to sort of big picture a bit. Okay, so this Tamsin also mentioned these socioeconomic pathways earlier, SSP. So this shows projected methane emissions under a scenario called SSP5. And again, as before, we can access a view of the underlying data. And we can see if we interact with the data that each year is responsible. Let me make it slightly bigger. Each year contributes to a single point in the output. So as I move my mouse around in this column, there's exactly 1 point of the original curve and of the moving average. Whereas if I switch over to emissions, I can see each emissions value contributing to a single point of the original curve and 3 points of the moving average. So what that's kind of revealing to us is the window that's being used to compute the moving average here. And we might conjecture that there's a window of size 3. And if we go over to the other side, we can interact with the chart. If we pick one of the points in the original curve, we just pick out a single value. If we pick out one of the points in the moving average, then we see indeed that 3 points were being aggregated in some way. And again, this is impartial, it's sort of incomplete information. It doesn't tell us that these 3 numbers were added together and divided by 3, for example. Hi, Jesse. Okay. So yeah, so this isn't anything like a full explanation of moving average. This is just giving us a bit more kind of visibility into what's going on. Okay. So here's the source code for moving average. Similar observations before, there's no mention of any of these interactions here. So the algorithm just does what it does, and that kind of relationship between input and output is just kind of surfaced automatically for the user. So let me show you now what that looks like if we actually change the way the algorithm works. So let me open the moving average example. So this is the code we were just looking at, and I'll give it this constant here, number 1, is telling us the size of the window that we're using to compute the moving average. So this is saying that the window has a size of 1 on either side of the central point. So let's see what happens if we change this to 2. Okay, if we rebuild or kind of republish the web page and reload the figure, we'll see that we get a smoother curve now than we had before, which is to be expected because we're using a bigger window to do the averaging. But we also see there's a slightly different profile now. So if I pick one of the points on the right, we can see that 5 elements are being pulled in on the left. So we didn't have to go and program that change. We didn't have to think to ourselves, how's this interaction going to work? What kind of JavaScript am I going to have to write to sort of implement this interaction? How am I going to, where have I hard-coded that constant 3? Well, it's not hard-coded in, it's just surfaced automatically through the way that the dependencies are tracked. Okay, so the key ideas really in these 2 examples is that we want to think of or support the idea of comprehension, hi Ali, by the way, as an active process of hypothesis formulation and testing. So in other words, as I'm trying to understand something, I'm not just a passive participant. I actually have conjectures that I'm formulating in my head about what things mean and what they represent. And instead of having to just kind of run through those ideas in my head, perhaps sort of implicitly, I'm able to actually test them out and formulate kind of experiments of my own. And those experiments take the form of interactions that I can make either with the chart or with the underlying data, and I can see what those relationships are. And as we saw with the moving average examples, implementation details then start to matter because they start to become sort of apparent to the user in some cases. And one of the kind of working assumptions here that we haven't kind of really challenged is the idea that this does actually improve comprehension. So, we're hoping that this is going to sort of at least not make things worse, although I think it's not hard to imagine situations where, you can sort of overload people with information or people can get confused because there's so much being presented. But yes, we need to do some kind of user studies, and we've got some planned for later in the year. And it'd be interesting to see sort of the extent to which this can actually help with comprehension. And again, the sort of overall picture is how can we break down this this kind of disconnect between the world in which we do science and the world in which we communicate science? Can we kind of collide those two worlds together a bit? Okay. So so the third example is going to take a slightly different tack. So I might just let anyone jump in with any thoughts or questions they might have at this stage. Any thoughts? Any observations? Go for it.
I might know the answer to this, but are you considering using LLMs to evaluate the comprehension?
Yes, that is something we talked about. Yeah. Yeah, like Jonathan's one. Yeah, yeah, I think that's a really good idea. I think we want to do human ones as well, but it would be an interesting kind of reference point to have the LLM-based ones as well.
So that's asking the LLM, what do you want, like, what's the meaning of this thing?
Yeah. So there's the thing that Jay was just alluding to is some studies that have been done using LLMs for kind of visual comprehension of charts. So that they're presented with charts and captions and asked to make sense of the data essentially and explain what they're kind of looking at. And they can do quite well. But I suppose the question then becomes, how much better can they perform if they're given some kind of more fine-grained information about how inputs and outputs are related? And also, presumably, a lot of what the LLM is doing is kind of conjectural. You know, it's being driven by clues that are being provided in the captions and the natural language that comes along. So in those cases where the natural language is wrong or misleading or ambiguous, the LLM might make the wrong inference. Whereas if we can surface some of the actual stuff that's going on inside the computation to the LLM, it's got more of a ground truth to act on. That would be the thought anyway, or the hope. Okay, right. So again, let's go back to this IPCC example. So policy reports and indeed scientific papers and articles don't just make claims using charts, they use text. So this text is really hard to interpret as well. In fact, in many ways, it's harder to interpret than the visual stuff. There's kind of complex uses of adjectives, sometimes in certain technical ways. There's things like iteration and this whole part relations, kind of mereological relations. There's all kinds of implicit referencing, so things like anaphor and cataphor. There are quantitative expressions that clearly mean something very specific in terms of the data. Like when we talk about things like total global warming, best estimate, and so on. So these things in just an opaque piece of text are just sitting there as words, but at the point at which they were authored, they actually meant something to the author. So can we actually, and our research question is asking, are there ways in which we can allow this supporting text to be transparent in the same kind of way that we've been talking about for visualizations? So this means making text that's itself kind of data-driven, self-explanatory, and more sort of verifiable, if you like. So I'm going to show you a kind of bit of work in progress for this one. So I'm going to switch to a different repository. So I should have said, by the way, if you want to follow along with this example, if you happen to have Node installed on your machine, then this is very easy to run these examples. You can just go to this template repository, fluid article, and the GitHub organization is called Explainable Viz. If you go there, if you clone the repository, you can just do yarn install and okay, I already had it installed, but if you've got yarn and node installed, then it should be relatively easy to get them going. And then yarn bundle serve will build the website and deploy it to localhost. So you should be able to try all that out. Okay, so this transparent text idea, I'm going to switch to a different repository. I'll just build the website for that. So, oops, go to this example. Okay, so this is a kind of extract from a scientific paper that's reporting on the performance of some machine learning models. So as you're probably getting used to now, there's a way to see the underlying data set. If I click on this little icon here, I can see a view of the underlying data. So the difference here is that rather than the charts being linked to data, what we've done is link some of the words in the text to data. So for example, this paragraph is making some kind of claim about accuracy is improving, but it's not clear what accuracies are actually being referred to here. This is a comment about training time growing, but the accuracies themselves are not mentioned. But if we move our mouse over the word better, we can see that it was these two numbers here that were being compared. And we've also got this kind of related outputs idea that I mentioned earlier, where we saw that there were segments in the bar chart that were related to points in the scatter plot point, and they were related because they had intersecting data consumption. So the same thing's going on here. So if, for example, I move my mouse over growing, the text in this case makes it quite clear that it's 99 and 106 that are being compared, but I can also see that larger is somehow related, and I can investigate that by again kind of moving my mouse over larger and seeing that it's 207 is being compared with 106. So it's kind of not obvious from, unless you actually start parsing the sentence and thinking about the grammar of the sentence, what this kind of larger is actually referring to. And indeed, if we interact with larger, we can see that shorter is also related. And if we look at shorter, then we can see that shorter 65 is actually being compared with 207. And in this case, the implicit reference, shorter takes two arguments, and one of those arguments is implicit, and it's not obvious what that argument is, and it occurs 4 sentences down in the paragraph. So there's quite a lot of ways that it's possible to get confused about what you're reading, to misinterpret things, or if you're the author, to sort of explain things in the wrong way. So the idea here is, can we make text that's a little bit more transparent in this sort of way? And I'll show you what this looks like in Fluid in a second, and then the current implementation is quite naive, and then I'll talk a bit about how we can improve it over the next few months. So just one last thing to show here. So these two words, smallest and lowest, are related here because they both depend on the word, on the string CNN, essentially. Okay, so what does this actually look like in Fluid? So at the moment, So at the moment, the way this works is you take what would otherwise be just a plain paragraph of text, and you replace fragments that you kind of think of as somehow data-driven by expressions that compute that natural language from the data. So you replace kind of literal text by queries that evaluate to those literals, essentially. And in this case, we've got a sort of library of helper functions that do some of that mapping to natural language. And there's many kind of interesting questions that come up about this approach. So hopefully we can have a bit of discussion about that for anyone interested in any aspect of it, including the natural language part. So you might be wondering, this doesn't look like an especially practical way to write a scientific paper. If you have to program your paper and you're going to write a whole, this summary for policymakers is a 30-page document with a lot of figures and tables. Is it going to be written in this style? That seems unlikely. But there's a couple of ways in which I think we can start to address that. So let me come to that in a second. First, what I want to do is kind of clarify that the potential value of having this kind of data-driven text in the first place. So the key point is that if we were to evaluate this piece of text on a different data set, or perhaps with different definitions for some of the analyses, we'll actually get a different piece of text. So that's kind of what we mean by the idea that it's data-driven. So for example, if I do this comparison of accuracy the other way around by swapping that operator, and I rebuild, and now go back to the website, then you can see that where we had lowest, we now have 15th lowest. So 15th lowest is a bit weird. 15th lowest actually corresponds to highest here, but that's just because there happen to be 15 pieces of data that are being compared. But yeah, the point is that the meaning of the text changes as you evaluate it at different positions in the data, or in different, if you swap out the analysis, you'll get a different piece of text. So, or if we were to swap these two kind of model values around when computing trend word, then where previously we had outperforming, we've now got performing worse than. Okay. So that's the kind of very high level idea of what we're trying to do with this transparent text. And the idea is that like visualizations, text can also be bidirectionally linked to the data that's relevant. So we see there as being two kind of potential use cases for this. So one is what I've already been kind of alluding to, which is the idea that as an author, you might want to create an article that's integrated with its evidence base rather than just a kind of piece of static text. And that allows you to actually make supported claims that are backed up with data and queries rather than just claims that have to be taken at face value. But there's another potentially interesting use case here, which is you could imagine there's a piece of data science that's already been done. So this is maybe similar to the scenario Jay was talking about. So you might be reading or reviewing an article, and I want to make sense of that as I'm reading it. And rather than having to keep all that sense making in my head, maybe I can actually externalize some of that interpretation of the text as computation that generates the text from data. So I'm retrofitting a kind of interpretation of the text to the data as I do it. And one of the things that might allow me to do is discover inaccurate or inconsistent uses of technical language, for example. So in the example we were looking at, just jump back to this one for a sec. So if you remember that the significantly better, like now we can see that these two values are being compared. It's not entirely obvious that the word significantly is fully justified there. I don't know. There's obviously no sort of definitive answer to the question of, is this 1% increase in accuracy significant or not? A lot of that depends on a whole host of other suggestions. But the thought is that by kind of making text more transparent, you sort of surface these sorts of questions or these sorts of considerations, which in an opaque version of the text, they might just not come to mind at all. So that's what I mean by kind of discovering perhaps inconsistent uses of technical language. You might, for example, see that in one situation, they said, yeah, this is really significant change. And then elsewhere, they've described it as a small change, but actually the range of change is perhaps bigger in the case that's not being described as significant. And that could be misleading. It might not be something that someone's done on purpose. It might just be something that happened by accident. But by kind of sort of systematizing how we interpret formal documents, there's a potential to discover these sorts of issues. So the working hypothesis that we have for this project is that there are three key ingredients to make this kind of practical and useful. So the first is this idea of data-driven text that I kind of showed you earlier with the Fluid program, where you actually compute fragments of text. And then to make this kind of worth doing in the first place, you need to have programming languages that are transparent, that are able to expose to a reader of the final artifact the kind of fine-grained relationships between inputs and outputs. Otherwise, you've just got a program that computes some text. But if I can't actually query the running of that program, then it's kind of much less useful. So kind of see this as a crucial step to making this worth doing. But as we saw with the kind of paragraph of text, there are a couple of things about that aren't very feasible. So let's go back to the VS Code for a sec. Yeah.
Yeah, over along with it full, or I had no problem running it, so I step through it.
Well, yeah, I think there's probably time. Yeah, go on. What did he do?
The Yarn Fluid Bundle website -w, the dollar website name.
Yeah.
No matter what I choose for that, it seems to not like it.
So what did when you put Yarn bundle website?
Is there a particular website name you choose much or-
If you wanted to, if you just do article, I think it should work. Minus W article.
That did work.
Okay, cool. Yeah, so there's a template repository, as I mentioned, Fluid article, and it has a single website within it called article. And
Place that on the slide.
okay, cool. Yeah, thanks for that. Okay, so yeah, so we already kind of noted that it's not really going to be that feasible to sort of write a big document like this. So I think there are two ways we could think about sort of improving things. So the first is a kind of easy one, but quite important. So it's the idea of interpolation. So you've probably seen that for string interpolation in languages like Python and JavaScript and so on. So what you can imagine is a kind of document authoring system where you just write your text in plain language, just as a big paragraph or sequence of paragraphs as normal. But when you want to produce a piece of text by computation, then you escape back to a programming language. So in JavaScript, that would be using dollar squiggly brackets. I think in Python, it's probably something similar. Or if you've used the kind of the F string notation in Python, you'll have seen a similar kind of interpolation type syntax. So we've got a kind of in-progress implementation of that. I'll show you that in a second. So that's a kind of relatively easy win. But I think perhaps a bigger challenge for this idea is just the idea that you're actually going to have the time or disposition to actually go through your text and sort of turn it all into a program like this. So a key part of this project is looking at an AI, a generative AI based authoring tool that would basically allow you to write fragments of text and then perhaps highlight a fragment of text that you want to turn into a kind of data-driven piece of text. And the LLM will then synthesize the corresponding expression based on the data sets that are available to it and replace that text by the corresponding expression, which evaluates to that text. And because we've got this transparency feature in Fluid, as well as that potentially being useful to readers, the transparency feature, here it can also help authors as well, because obviously one of the worries as an author, if you're using an LLM-based authoring tool, is that the LLM's generating kind of the wrong query for corresponding to your natural language. Perhaps you've left something a bit vague, or you've kind of underspecified the problem or something, or it's hallucinating for some other reason. And so because you've got this ability to interact with the result and actually see what data is being consumed, you've got at least one way of checking that the LLM hasn't produced complete nonsense. Okay, and there's a whole bunch of natural language questions, I think, that come up here. Luckily, LLMs are very good at natural language, so I think they are going to be able to play a role in this kind of tooling in various different ways, I think. So we can talk about that. Okay, I'm going to move on to the last example now. So this is a slightly different use case than what we've been considering up to now. So the observation here is that we also use interactive graphics to educate. So Google Brain had this great journal called Distill, which is still available online, but it's kind of been in hiatus, sort of semi-permanent hiatus for a while. And it publishes long form essays explaining challenging technical ideas. So things like convolutional neural networks, for example. So let me just show you what this particular example looks like. So if you go to the Distill website, you can see this example. So this explains the kind of basis of convolution, how it works, but it does so using a kind of funky interactive graphics thing. So I can move my mouse around on the kind of the input to the convolution. I can see how that's kind of interacting with the filter or the kernel and so on. I can't interact with the filter or the output, but it's still giving me quite a lot of information about how the data kind of flows through the computation. So this is all fine and dandy, but it's actually a bespoke JavaScript graphic that took presumably quite a lot of effort to implement. And from reading about this publication, this journal, it sounds like the reason it's in this kind of semi-permanent state of hiatus now is because essentially the huge amount of work that's required to produce these artifacts. So There just hasn't been a kind of big enough throughput, essentially, of articles to justify its continued existence. But the things that are there are really, really lovely, and I do recommend checking them out. So what I'll show you now is potentially how a transparent programming language can help remove some of the burden on authors for creating this kind of thing. So yeah, these things are sometimes called explorable explanations. So let's switch back to the Fluid article repository again. Okay, so if we now run this example, which hopefully will be just about big enough. Okay, so we have an implementation of convolution in Fluid. I'll show you that in a sec. But as before, we can open up the kind of underlying data. And in this case, the underlying data is just the input image and the filter that was used to do the convolution. So we can interact with parts of the output. So unlike the kind of hand-coded JavaScript, which only had the flow in one direction, here we can examine it in either direction. So for example, if we move around the center of the output, we see that we're using all the filter. Oh, hang on. I wonder if I've got the wrong version. Maybe I need to. No, I think we're okay. Yeah. So yeah, as I move around this central region, we're using all of the filter, but we're only using part of the input image. And the reason we're not using all of the input image, obviously, is partly down to the shape of the filter, but we're also missing off these corners here. And that's because of the zeros in the filter. So we might then kind of conjecture or wonder, let's say, what happens if we go to the edge of the output. And here we see part of the filter is no longer relevant. So we might at that point hypothesize that the reason that the filter becomes irrelevant when we reach the edge is because the input image is behaving as though it's being padded with zeros, similar to how the presence of zeros in the filter kind of cancel out the relevance of the parts of the image. So we can test that using the kind of sort of interactions we had previously. So we could, for example, make that into a persistent interaction and then go over to another element on the kind of opposite corner and see that we get a sort of different behavior. So this is again the idea that we can sort of formulate a hypothesis about what we're actually looking at. And instead of having to just sort of simulate the system in our own heads, we can sort of interact with a kind of running version of it and see what happens. So in this case, we might wonder, okay, so if that's the query that corresponds to that, that's the input, if you like, that's needed for this particular output element, what's likely to be needed for the two in the top right corner? Anyone want to hazard a guess? So if I put my mouse over 2 in the top right, what are we going to see? What parts of the filter are needed? Given what we needed for this, what we needed for that. Anyone have a guess? Yeah, so is that what you meant? Yeah. Yeah, so and then we can sort of carry on sort of playing around, and so we might sort of wonder whether that's symmetric, so if I do that and I go to the opposite corner, and indeed it is, and that's helping us understand how these components are coming together to produce the thing that we're actually looking at. So it's not a full explanation of matrix convolution by any means, but it's telling us something useful. And we can sort of play this game in the other direction. We could, for example, highlight a couple of points in the output and then move around in the input. And here we can see a kind of interesting mathematical property of the way this sort of dependency information works. So if I move around in any of the white bits of the output, then what I'm seeing on the right is all the data or the output that demands this piece of input. But as long as I stay within the kind of unselected parts of the output, then the data that needs me is also going to be disjoint from the things that I'd selected in the output. So if I stick to white cells here, I'm only going to be highlighting white cells on the right. And then the converse of that is also true. So if I go into the green area, then there's always going to be a non-empty intersection. There's always something in the data that's consuming 15 must at least include my original output selection. So we can see that here. Okay, so let's go back to the slides a sec. Okay, so this is what the code for convolution looks like. So we've got this this funny kind of bracket here, which is what we call a matrix comprehension. So it's similar to a list comprehension, but what we're doing is we're specifying the element that occurs at each position in the matrix. So we're saying for every n prime, use this expression in the middle to compute that element of the matrix. And actually we can see that the way we compute the inner matrix is actually compute each element of the output is by calculating a little 3x3 matrix for that element and then taking the average of those values. So we basically calculate the little 3x3 matrix corresponding to the kind of region of the filter around that particular input cell. We sum up those values and then divide them by the area, which is what this quotienting thing is doing here. So if we look at that in Visual Studio, actually, it might be a bit easier. So there's one more thing, or a couple of features that are kind of work in progress that I'm going to show you using this convolution example. So we made this observation that there is an intermediate matrix associated with every output element. So what we can do is we can attach a little piece of documentation to that intermediate matrix. So if we say something like average these to compute element value. Right, if I now rebuild the website. It's gone. Okay. So I need to attach the comment to the actual matrix itself. Okay. So now if I reload this, it should work. Yeah. So now if I move my mouse over a particular output element, what Fluid is going to be able to do is decide that you're interested in that output potentially as well. So for each individual output of the final convolution, we can now see the intermediate matrix that was used to compute that value. So this matrix was the value that when we added those values together and divided by 9 and rounded, we got the value on the right. So one thing we can do is we can use this interpolation syntax that I mentioned earlier that we want to use for the transparent text. So what that allows us to do is so because there's one of these matrices for every value of n prime, we can create an expression where we mention n prime and n prime in the actual piece of documentation. So now if I interact with the output, I'm going to see the actual particular coordinates of the output element that are kind of being shown for this intermediate matrix. And that's giving the user a little bit more context about what's going on. And let's say, for example, I select 2 of those, then I can see that they have different, one says 2,4, the other says 4,2. So that's showing us that there's one of these intermediate matrices for each output element of interest. And actually we can interact with these intermediate things as well. And what happens there is we see the upstream and the downstream dependencies. So this is showing us that each of these elements, each element in one of these kind of intermediates is contributing to just the highlighted output element on the right. And in this case, it's just the one element on the right, but each is being derived from two elements on the input. And in this case, it's just multiplying them together. So for example, this -12 was calculated by multiplying 6 and -2. So we're still not there with a fully kind of self-explanatory version of matrix convolution, but hopefully this gives a sense of kind of what a self-explanatory version might look like, because we haven't really had to do much work here as a programmer. We've really just had to add that dot comment in, and we've kind of got this user interface for free, essentially. So that interpolation syntax I showed you is something we're now planning to sort of backport to the transparent text system as well. Okay, so as before, the emphasis was on this idea of being able to kind of interrogate the kind of artifacts. Different implementations of algorithms exhibit different dependency profiles, and by interacting with them, we can learn how those algorithms work potentially. And the key point here is that this is a transparent algorithm rather than a handcrafted visualization explaining a transparent algorithm. So it's like starting at the other end. You start with the algorithm and you try to make it more self-explanatory. And in particular, the ability to see intermediate values really opens up the computation and allows the user to see more what's going on. And we also attached first-class documentation to these values. And by first class, I mean documentation that's actually computed and might contain computed content of its own. So for example, you could imagine attaching some of this first-class documentation to a table and then embedding in the documentation an appropriate visualization for that table. So then you could have a pipeline where if I select some output of interest and the table becomes relevant, when I see the table, instead of just looking at a plain table, I could look at a histogram, for example, of that table. So it's kind of similar in flavor in certain ways to notebooks, kind of what we're talking about here, but the idea is to build a kind of more flexible system where the reader of the system is in much more control of what they're actually looking at. And we think this has potential applications in sort of science education as well as publishing. Okay, so that's the end of the kind of demo part of the talk. So I've probably got about 10 more minutes or so where I'm just going to wrap up and talk a bit about what we're doing next. Does anyone else want to come in with any thoughts or observations, questions?
Very interesting how I love the idea of when you interact with you read a paragraph, then you want to know more about it, then you hover over the text, and then it gives you the raw data. So for me, the idea of like you have data and then you derive some statistics out of it, so that you don't have to go through the whole data. But this idea of going back to the data, as I'm just thinking about like who would be interested, like for example, if you're a subject matter expert, and then you think that, for example, you showed about significantly. And what do you exactly mean by significantly? Hopefully, then go to the raw data and delve further. I mean, do you have some application in mind where it can just revolutionize things, like where, for example, I don't know, like for journalism, how would it help? You mentioned, like where it can have the maximum potential.
Yeah, I think we're kind of still at the early stages. It's quite a rich topic because it's kind of this intersection, I think, of sort of generative AI, which I think is a kind of an enabling technology that's needed to make this kind of practical. It's this kind of provenance-aware programming languages. There's a data visualization element. There's natural language processing and so on. So there's a lot of different axes of stuff going on. But yeah, I think kind of there's probably a continuum between sort of heavy domain expert style users and kind of lay users, which I'll actually come to in a bit. And I think kind of understanding where we might sit on that spectrum or where you could sort of have most impact early on is still a bit unclear, but yeah. I mean, so the point you made, or kind of one issue I think that comes up is that if you reveal a lot about the underlying data, it can be quite confusing and overwhelming to people. So thinking about how to kind of have sort of like a kind of gradual, on-demand discovery of additional detail as you need it. So most of the examples I showed you at the beginning were kind of, you have a single output and a single input. But where we're moving towards with the matrix convolution example is where you could potentially work back from the output and unpick it and reveal more detail. So in data visualization, there's a really interesting topic called disaggregation, which is, you may know about, but it's essentially where you go back from some kind of aggregate or summary view of data to the raw data. And there are kind of there's a whole cottage industry of plots that are designed to sort of support these kind of views where you want to sort of summarize something and also provide information about the distribution. So one idea here is that rather than thinking of those decisions as always kind of hard-coded in, that you could provide affordances that would allow the user to actually do disaggregation themselves, but in an incremental way.
It's like chat with your papers. You have a paper and then like, okay, I really want to know where this graph is made, like what data is being used to make this graph.
Yeah.
And then you're kind of chatting with paper and then you get more data insights and then you can dig deeper.
Yeah. Yeah, exactly. And there was an interesting study that I was just looking at the other day where they were kind of using LLMs to recreate figures and so on in papers. So I think that's a kind of similar use case where you're reading something and I want to reverse engineer a tangible understanding of that thing, not just an understanding in my own head, but an actual computational artifact that reproduces the thing that I'm looking at. And then if you can make that thing transparent and explorable as well, then as well as reproducing it, you've got a kind of interactive version.
You could get publication started with Explainable. And I see research papers getting more like in the shape of a blog rather than research paper. You just interact with research paper.
Yeah, that's a good point. And I mean, and another thing I'm going to come to in a second, which I think is related to what you just said, is the idea of kind of science being more kind of incremental itself. So instead of having to sort of spend months writing a paper and then you just throw your paper over the wall and sort of see what happens, it's a much more interactive process. Interactive in this sense, but in the more human sense of it's a kind of dialogue going on between you and reviewers. As a reviewer is kind of understanding what you're doing, they may be coming up with suggestions about that actually become part of the final science. Yeah. Okay. Right. So let me move on. I'll come back to some of those questions in a minute. So there's a couple of ways in which we're thinking about sort of how we might move this forward, how in terms of having impact and so on. So, okay. So one question is, okay, the world runs using Python and R and Julia and all that kind of stuff. So how can we sort of make this kind of idea of programming languages that are more transparent into a more mainstream idea? What are the actual prospects for doing that? So there's a couple of different ways, but there's probably many ways you could approach this, but there's a couple of I'm going to mention now. So the first that we're going to try anyway with Fluid is to make it more like Python. So this would be just a fairly low level change. It would just be a change to the syntax, but we've done some kind of initial experiments and we think we can probably switch to something that wouldn't be a superset or a subset of Python. It would just be Pythonic. So it would just have some of the flavor of Python. And we could have libraries that kind of emulated the interfaces of commonly used libraries and so on. And I think that would help people kind of try it out and play around with it. But also, I think it would make it an easier target for LLM code generation as well, because the syntax is just going to be a bit more Python-like. So, for example, we can use the sort of lambda keyword for anonymous functions. We could use this kind of for in notation for list comprehensions. Things like def for defining functions and indentation sensitive parsing, so we don't have to have semicolons everywhere, things like that. So that's a sort of low level thing. And of course, you might say, well, why bother going to all the effort? Why not just take a different tack and actually try and make this dependency tracking part of Python itself? That seems like that could be a super cool thing to do. The problem there is just that Python has a big kind of core dependency on C. It's just the way it's implemented, and libraries like NumPy and Pandas and so on have kind of are substantially built on top of C libraries. So the problem there is that you might solve the dependency tracking for Python, but then you'd have to solve it for C and push everything through in a kind of compositional way. And that's just probably going to be basically not feasible in practice. So a different way to approach it would be to take a language like Julia. And then I think then there are some prospects for adding dependency tracking directly into the language. So it's a newer language. It has a more extensible compiler. It has this kind of macro facility that's quite powerful. It would still be quite a big engineering effort. So I'm not sure whether this is, something we concretely want to do, but it's certainly one of the directions that you could look at, I think, if you started to want to think about what would it take to make some of these ideas more mainstream. So with this kind of approach, you'd want to come up with some kind of zero cost abstraction. So that means a feature that if you don't use it, you don't pay any cost for it. If you do use it, then it might come up quite, but that would be okay because you'd gain some benefits. So in this case, you'd probably have to, for example, recompile your entire application, including all the third-party libraries and so on that you use with this compiler extension enabled, because otherwise you get something similar to the problem with Python. So the problem with Python is if you could change the Python VM to do the dependency tracking, the minute you call out to a C library, that information is lost. Same thing with third-party libraries in Julia if you didn't kind of compile them with this extension enabled. So that's kind of one thing we're looking at. And then the second kind of bit of kind of current future work, so it's not future, it's sort of on the immediate horizon, is something we call computational transparency. So what I've mainly been focusing on so far is data transparency. So that means for each piece of output that I care about, what's the kind of least set of inputs that I need in order to account for that part of the output. So we saw that with these selections going back and forth. So computational transparency is a way of extending that to kind of computational explanation. So it's saying whenever you have these two sets of inputs and outputs that are related, can you provide a kind of executable subprogram that actually reproduces that part of the output given that part of the input? So this is kind of what it might look like. So this is a mock-up. It's inspired by spreadsheets, but I think there are a lot of choices about how you might go about implementing this. But so here what's happened is in the mock-up, the users selected a bar in the bar chart. And as well as showing them that these four numbers are relevant, we're also able to show them that we added those four numbers together. And in the right-hand chart, the user selected some points and we're able to show them that each point was calculated by sort of dividing the values from two other columns. So this all looks kind of cute, but for there to be any prospects at all for this to work, I think you would actually have had to have implemented these programs in quite a different style. So if you implemented them in a kind of naive sort of Python-like style, where you just have a big loop over the data, for example, it's not clear that you're going to be able to easily extract these nice abstract summaries of how the data was manipulated. On the other hand, if you'd written it using a kind of something like NumPy or Pandas, then where the operation is much more at the structural level of the data, then you may be able to kind of pull out these sorts of high-level views. So for example, in Pandas, you can do things like column-wise operations. You can say, compute a new column by just dividing these two columns together, and that's an operation that makes sense. If that's how the program is expressed, then you could actually surface that directly to the user. If it's only indirectly obvious that that's happening, then it's not clear that there's a way to sort of detect that. And also on the left, we're doing things like, we're taking a multi-dimensional structure and kind of crushing it along a dimension. And you might implement that just with a for loop, then it's going to be quite hard to sort of detect that that's what's going on. But if you've got a library of array operations and you've expressed it directly as a roll up along a dimension using an aggregator, then you're in a better position to kind of surface that to the user potentially. So this is what mathematicians call intentional information. So the extensional information is the kind of I/O relationships between inputs and outputs. This is the I/O relationship enriched with information about how that relation comes about. So this is kind of intentionality. And the idea would be to go back, to have those kinds of things we saw earlier, like the BBC visual journalism article or the climate simulator, and have a version of that that's much more self-explanatory. If I can actually see what calculations are being done, then the kind of reason for a particular outcome is going to be much easier to understand or challenge if you don't agree with it. Okay, so going beyond what we're currently working on to kind of some of the questions you were asking about. So I think one interesting continuum that there's been quite a lot of talk about sort of breaking down in recent years is the kind of distinction between just passively consuming content and kind of actively consuming and then actually creating as well. So if you're a reader, you're kind of at one end of this spectrum in a sense. You're kind of an end user of the technology. You want things to be responsive, intuitive, informative, and so on. We want there to be a continuum between being a kind of passive reader and a reader that's able to actively engage by, for example, clicking on things. So that means opportunities for interactions should kind of present themselves. It shouldn't be something you have to discover. And at the other end of the spectrum, you have authors who are kind of technology specialists. There's a kind of downside, which is that they're invested in specific workflows and technologies and so on. So the benefits of any new system need to be obvious and the barriers to entry need to be low. And of course, these aren't, we're not necessarily one or the other of these people. We're occupying different points on this spectrum at different points in the day, depending on what we're doing. But the idea is, can transparent languages help kind of make it more of a continuum that we're talking about here? And if we look at what that might look like in the context of, say, peer review, then I think you could imagine a world where, as we were just saying, a reviewer, it becomes closer to a collaborator, so I may interact with this artifact that you've sent me as a paper. I'm kind of critiquing it. I'm formulating queries by interacting and so on. If I find something of interest, it could be I've done a different analysis on your data or I've changed some of the data to see what happened. If I've reached an interim interesting conclusion, then that should be something that's persistent that I can share with you as a URL. You ship your paper to me as a URL, I give you back another URL that says, okay, here's an interesting query. What do you think? And then that becomes part of a conversation. If there are new observations being made, they become part of the actual science. Whereas now kind of a reviewer, at least in several disciplines, reviewing is still kind of a secondary contribution. I know it's moving away from that, but I guess the question we're asking here is kind of what are the enabling technologies that are going to allow that to be broken down more quickly? And you might have come across ideas like continuous science, agile science. More recently, I've heard people talk about composable science as well. And I think that this kind of fits into that overall picture. Okay, so just a final wrap up. If you wanted to try Fluid for yourself, you've sort of got a sense of what the language looks like. You might have a kind of open access publication with figures that you could re-implement in Fluid to see what that looks like. You might have some questions about prior work that you didn't get to ask, you might want to revisit, or you might have something new that you think you could present in an interesting way, as long as it's not a sort of super data intensive. So it's a research language, it's very much work in progress, so we can only really work with simple examples at the moment. But we've got some ideas about how we can make this kind of scale a bit. If it has an obvious visual component and would benefit from being presented in this kind of open, explorable way, then do feel free to get in touch or tell us what you've got in mind. And there's a bunch of people who worked on this, a couple of whom are here, and I've got some funders to thank as well from kind of earlier incarnations of this project. This is where you can reach me if you want to talk about anything, and I think I will stop there.